19% of Mars was once covered by a massive ocean holding over 20 million cubic kilometers of water. This ancient body of water contained more liquid than Earth's entire Arctic Ocean. While scientists long suspected Mars had water, recent discoveries show the planet wasn't just wet. It had shorelines with sandy beaches formed by wave action. For decades, the evidence of Mars' ancient coastlines remained hidden beneath the surface. Now, groundbreaking radar technology has revealed compelling evidence that fundamentally changes our understanding of the red planet. Mars' ancient shorelines provide crucial insights that will transform our approach to exploration and our search for evidence of past life. As we advance our plans for human missions to Mars, these discoveries about its watery past will guide how we explore this fascinating neighboring world. Geographic features resembling shorelines were first observed by Viking orbiters in the 1970s, near the Martian poles in regions like Arabia and Deuteronolis. The northern hemisphere, particularly areas like Aeolis Dorsa, shows definitive evidence of a massive ancient ocean. Substantial sedimentary accumulations and the planet's hemispheric dichotomy, with a significantly lower and flatter northern region, created the perfect accommodation for a large ocean basin. Chemical properties of Martian soil and atmosphere further suggest conditions that could have supported liquid water in the past, which is crucial for the existence of oceans. China's Zhurong rover deployed ground-penetrating radar capable of scanning 80 meters beneath the surface. The rover traversed 1.9 kilometers along Utopia Basin, using radar to beam radio waves into the ground. These scans revealed smooth, gently sloping layers of sand approximately 10 meters below the surface, parallel to a rocky cliff and rising toward it at a shallow slope. The reflections from these waves provided detailed data on subsurface features, enabling scientists to make their groundbreaking interpretation. Scientists conclusively ruled out alternative explanations for these formations. The structures were not sand dunes, impact craters, or lava flows. Their orientation and slope definitively identify them as beach deposits formed by waves. This discovery provides strong evidence for the existence of the Deuteronolis Ocean, indicating that Mars once supported liquid water for extended periods. The presence of networks of gullies and channels resembling ancient riverbeds on Earth further supports the ocean hypothesis, suggesting a comprehensive hydrological system once existed on Mars. Beach formation on Mars involves similar processes to Earth, operating under different environmental constraints. Wave action transported sediment and deposited it along shorelines, creating the characteristic sloping sand deposits discovered by Zhurong. On Mars, these processes were influenced by weaker gravitational pull and a thinner atmosphere, altering the dynamics of sediment transport and deposition. Longshore drift, the wave-driven process that moves sediment parallel to the shore, contributed to beach formation on Mars, though differently than on Earth. Mars experienced minimal tidal influence due to its small moons, which lack the gravitational force needed to generate significant tides. Wind likely played a proportionally larger role in shaping Martian beaches despite the thin atmosphere. Mars' current atmosphere is approximately 1% of Earth's thickness, yet still generates sufficient force to move sand over long periods. The presence of sandy slopes indicates a past environment with active geological processes, including water flow and wind. These beach deposits suggest that Mars had environmental conditions substantially different from today's cold, arid environment. Rivers would have fed the ancient ocean, and waves would have distributed sediment along the shoreline, forming beaches. The sediment supply on Mars would have come from ancient river systems and erosion of Martian terrain, though these processes would have been slower and less intense than on Earth due to the planet's smaller size and lower gravity. Water dramatically shaped Mars' surface through erosion and deposition, creating valleys, channels, and lakebeds across the planet. Rounded pebbles and dry riverbeds and extensive valley networks conclusively prove strong water flow occurred in Mars' past. Water helped form distinctive geological features like gullies, slope lineae, and deltic deposits that persist on Mars today. These features suggest a watery past with rivers and floods that could have supported life. The ancient Martian water cycle involved the movement of water between the atmosphere, surface, and subsurface. Evidence of dramatic sea level changes, including a documented drop exceeding 500 meters, demonstrates this system's dynamic nature. Fan-shaped sediment deposits at the mouths of ancient rivers, like those at Hypanis Valles, confirm a complex water cycle with rivers flowing into larger bodies of water. Water vapor in the atmosphere would have contributed to weather patterns, potentially leading to precipitation and further shaping the surface. Several factors contribute to the preservation of these ancient water-carved features. Mars' low tectonic activity means its surface isn't frequently recycled like Earth's, allowing ancient features to remain visible for billions of years. The thin atmosphere results in less weathering and erosion, while the absence of liquid water today means erosion processes are significantly reduced. Mars' cold climate has helped preserve ice-rich features and prevented significant erosion in some areas. The mineral composition of Martian rocks can resist alteration and degradation, helping to preserve ancient geological features and potential biosignatures. For liquid water to exist on Mars, atmospheric pressure needed to exceed today's 0.6% of Earth's. Current conditions cause water to rapidly evaporate or freeze and then sublimate. Mars would require temperatures between 0 degrees and 100 degrees at Earth-like atmospheric pressure for water stability, compared to its current average of 67 degrees. The Martian atmosphere contains very little water vapor, which is essential for maintaining liquid water. The presence of salts like perchlorates could have lowered the freezing point and raised the boiling point of water, allowing brines to remain liquid at temperatures below 0 degrees. This is crucial for understanding how liquid water might have existed on early Mars. Additionally, geothermal heating from magma chambers could have provided localized conditions suitable for liquid water to exist beneath the surface, even under relatively thin atmospheric conditions. Atmospheric loss drastically impacted Mars's habitability. As the atmosphere was stripped away by solar wind and radiation, Mars underwent severe climate change. Reduced atmospheric pressure and temperature made liquid water existence impossible, transforming the environment from potentially habitable to uninhabitable for organisms requiring water and stable temperatures. Solar wind caused significant atmospheric erosion through atmospheric sputtering, solar particles colliding with the atmosphere, stripping away gas molecules. Mars lacks a strong global magnetic field to deflect these particles, allowing direct interaction with the upper atmosphere. NASA's MAVEN mission measured this loss at approximately 100 grams of gas per second, accelerating during solar storms. Extensive networks of valleys, channels, and lakebeds definitively prove Mars experienced dramatic climate change. These features, now dry and barren, demonstrate a transition from warm, wet conditions to the current cold, arid environment. Recent studies confirm Mars experienced ice age cycles with ice moving from the poles toward the equator and back again, suggesting climate fluctuations similar to Earth's glacial cycles. Carbonate minerals found in Gale Crater have isotopic signatures indicating extreme evaporation, suggesting these minerals formed in a climate that could only support transient liquid water. This points to a climate that fluctuated between wet and dry conditions. The transition from a reducing to an oxidizing atmosphere on Mars is linked to climate change. A reducing atmosphere could have supported a strong greenhouse effect, warming the planet, while oxidation led to cooling. Changes in Mars' orbital parameters, such as obliquity, have influenced its climate by altering the distribution of solar energy, leading to multiple climate transitions throughout Mars' history. Understanding how Mars's climate evolved is challenging due to limited data and observations, interpretation complexities of geological evidence, and modeling uncertainties about atmospheric composition and greenhouse effects. Mineral deposits including clay, carbonates, and sulfates found in locations such as Gale Crater provide decisive evidence of past water-rock interactions on Mars. Clay minerals discovered in Martian mounds formed in neutral pH conditions and low salinity water, an environment highly conducive to life. Their presence confirms Mars once maintained stable, liquid water bodies capable of supporting biological processes. Hydrothermal activity signatures in Martian meteorites reveal crucial information about Mars' watery past. The Black Beauty meteorite, NWA734, contains evidence of hot water dating back 4.45 billion years. The Lafayette meteorite contains idingite, a mineral formed through the interaction of olivine with liquid water at least 742 million years ago, possibly originating from subsurface ice melting due to magmatic activity. Alteration minerals like serpentine and saponite, observed in Martian rocks, indicate past water-rock interactions. These minerals are associated with serpentinization processes which could provide energy sources for microbial life. Secondary minerals like ferrihydrite reveal diverse redox environments on Mars, which could have provided energy sources for microbial metabolism, further supporting the planet's habitability potential. Ground-penetrating radar emits electromagnetic waves that reflect when encountering boundaries between materials with different properties. The Zhurong rover's GPR, capable of penetrating up to 80 meters beneath the surface, detected various subsurface features indicative of past geological processes. These features include structures consistent with past water activity, helping scientists build evidence for Mars' aqueous history. This technology offers significant advantages over other exploration methods. Its non-invasive nature preserves potential biosignatures while providing high-resolution images of subsurface structures. GPR operates effectively in various media and can be mounted on rovers for efficient planetary exploration. Despite these advantages, GPR faces limitations on Mars. Penetration significantly reduces in high-conductivity materials common on the planet. The technology requires balancing frequency and resolution. Higher frequencies provide better resolution but penetrate less deeply. Mars' harsh environment poses challenges for equipment durability, while data interpretation demands substantial expertise. Current life detection methods employ multiple technologies. Raman spectroscopy uses laser light to identify bioorganic molecules like lipids and amino acids. Mass spectrometry analyzes samples from microbial fossils, particularly in sulfate minerals. Nanopore sequencing can detect small amounts of DNA, while microscopic techniques could directly observe microorganisms. The discovery of ancient beaches critically informs life detection strategies. Shorelines represent prime locations for life's emergence due to the interface between water, air, and land. These areas are now priority targets for searching for signs of past life, with beach deposits preserving potential geochemical signatures of biological activity. Integrating multiple detection methods significantly increases the chances of finding life on Mars. Combining chemical analysis with microscopic examination and metabolic detection provides comprehensive evidence and reduces false positives. Future missions should strategically incorporate these diverse methods to ensure robust life detection capabilities. Future Mars missions will continue investigating ancient shorelines, subsurface water, and climate history. By combining disciplines like biology, geology, and atmospheric science, researchers can build a more comprehensive understanding of Mars's past habitability. International collaboration remains essential for advancing Mars exploration through shared resources and expertise. The discovery of ancient beaches on Mars represents an important advancement in our understanding of the red planet. These findings confirm Mars once supported conditions with oceans, rivers, and shorelines formed by wave action. As our exploration of Mars continues, these discoveries will guide our search for evidence of past life and potential resources to support future missions.